Okay, hi. Alright, so this is TE 303 class for the day December 5th. Although we are not there yet, I'm going to be gone, so I decided to record this video for our lecture instead of our lecture, I would say. And I would like to just immediately start today's lecture. Okay, so where were we? Let's remind ourselves what we have done up to now. In chapter 4 is a summary. In chapter 4 we looked at different amplitude modulation techniques: double sideband suppressed carrier, double sideband plus carrier, which is like regular amplitude modulation, single sideband. Again, you can use it with suppressed carrier or plus carrier, quadrature amplitude modulation, and vestigial sideband. And these are different amplitude modulation techniques. Each one has different advantages and disadvantages in terms of power efficiency, and so I'm gonna give you as a homework, okay, as a homework, compare these amplitude modulation techniques in terms of 1. Power efficiency, 2. Bandwidth efficiency, 3. Envelope detection, possibility, let's say, 4. Risk of crosstalk, distortion at the receiver. So why don't you think about all these aspects for these different methods of amplitude modulation, and then just make sure that you understand each one in terms of their power efficiency, bandwidth efficiency, envelope detection, possibility, risk of crosstalk, etc. Okay, so after that, what we have looked at in the last lecture, if you want to remind yourself, I can show you. We worked on the PLL, the phase locked loop circuit, which is used for locking the frequency, the input frequency. So you can have such a circuit as shown here, where the input is a pure sinusoidal function with a certain phase, and you want to generate the same sinusoidal function with the same frequency and the same phase. So you want to lock onto the incoming signal. Okay, so that's a circuit. PLL is a circuit which you can use for this purpose. And the need for PLL arises because of, for example, the Doppler effect, where the input frequency here, the frequency that you receive, even may not be exactly the same frequency that was sent to you by the sender or the transmitter. Why? Because you may be moving. So if you're in a car, if you're moving, then there will be a frequency shift due to the Doppler effect, and you need to lock onto the new frequency by using a PLL, for example. So what you need for a PLL is, okay, so again as a summary, phase locked loop is a circuit to lock onto a sinusoid's frequency and phase, so that you're really purely in sync with the incoming signal. Okay, but here, to be able to use PLL, you need a carrier. You need the carrier. So if you want to see this picture again, we assume the input is a pure sinusoid, right? So what if in some certain modulation techniques we do not send the carrier? So what if the input here cannot be the carrier, and if we don't have the carrier, is there any way we can obtain the carrier from the signal that's sent? So let's look into that and how we can use PLL in those cases. So that's the initial topic of our lecture today. And this is called carrier acquisition. So how can we get the carrier signal acquisition in double sideband suppressed carrier modulation? Okay, well, so we can use such a circuit. So since there is no carrier in double sideband suppressed carrier, we need to acquire it, right? We need to somehow generate it or something. Okay, acquire it. And such a circuit that I'm gonna draw here now will be able to do that. So we can use a signal squaring technique where we take the square of the input signal, which will generate some component at the carrier frequency. Actually the double the carrier frequency, so cosine omega ct. So this is the original double sideband suppressed carrier signal. Now if you square this signal, go make it through a squarer, so it's a non-linear circuit we are talking about here, and then obtain a signal, let's call it x of t, and then pass it through a band pass filter, but around 2 omega c, okay, at minus plus 2 omega c, because after you take the square, your signal will be at 2 omega c, okay. And then you obtain something here. Now we say that this something here is gonna be the carrier, double the carrier frequency, so cosine omega ct. So there will be some pure sinusoidal signal there. Now you can use PLL because now you have the carrier with you, and then after you lock onto this signal with the 2 times the frequency, you can use a 2x1 frequency reducer divider. Okay, frequency divider is the correct term, where you can obtain k times cosine omega ct, which is going to be the same as the input frequency. Okay, so now that you can use the PLL to lock onto the signal. So let's analyze this and see if this is really possible and why it is possible. Okay, so what is x of t now? That's after the squaring. So let's do the squaring now. Cosine omega ct square. So if you open this up, what you get is m squared t cosine square omega ct. Now this one, cosine square omega ct, can be written as 1 plus cosine 2 omega ct divided by 2. Okay, so now we can see that there is a signal component, and then there's another component at cosine 2 omega ct. Now the bandpass filter will get rid of the first term, so that's gonna be gone. So after the bandpass filter, after BPF, this term is gone. Then how about this term? Can we obtain pure carrier signal from this term? Well, okay, we know that the m squared t is always positive. So since m squared t is always positive, the mean value of m squared t, this is like the average value of m squared t, let's call this k, is gonna be positive, right? So I can write m squared of t as k plus some signal phi of t, let's say, where k is the average value and phi of t now has mean 0. So this phi of t is a signal with mean 0. Okay, average value 0. So So now I can see that there is clearly some carrier signal appearing in x of t. So x of t, we can write it as, okay, I'm gonna keep this m squared t over 2 because it's not gone yet, plus k cosine 2 omega ct plus phi of t cosine 2 omega ct. Okay, so now the bandpass filter should be tight. So if your bandpass filter is tight, this one really will not have a lot of components. Very little of this passes through the bandpass filter. This one passes, of course, and this is again is cancelled. It's not passing through, the suppressed by the bandpass filter. Okay, so so in the end what we get here is the input a k cosine to omega ct, because we can ignore this little component there for the phi sub t term. So so the signal at the output of the PLL, so at the output of the PLL, what we get is y of t equals k cosine 2 omega ct. Okay, so that's good. Now we generated the carrier, but at twice the frequency. Now we need to divide the frequency. We need a frequency divider to go down in the frequency. So this, how does this signal look in time? So what we generated here is, instead of cosine omega t, we generated cosine 2 omega t. So if you have to plot this, it's higher in frequency, right? So what you're generated is like this. So now you need a frequency divider which will generate this for you. Let me see. So yeah, so this is what you want. You want something with a smaller frequency. So this is your double frequency signal, y of t, which you can generate, so there's no problem. Okay, which is equal to k cosine 2 omega ct, and this one is k cosine omega ct. Of course, if there's a phase in the input, then it will also track the phase because you're using the PLL, so you won't have any problems. So you can verify that there's no problem in this circuit. So this is one approach. You can generate this carrier by the signal squaring. Another approach is a circuit called Costas loop. Another approach is called the Costas loop. Okay, and this is a circuit for, again, coherent demodulation, so that it locks onto the incoming double sideband signal. So now let's see. If our input signal is this, I will draw you the circuit here. M of t cosine omega ct plus theta input. Okay, so there's a phase, and we don't know this phase, and we want to generate the same signal at the same phase, the same carrier actually. So this is the carrier part, right? So this is the carrier part. Since it's multiplied by m of t, we don't have it separately, so we need to generate it. Now this is such a circuit. So you need a multiplier here. Okay, Now you have a VCO here, a voltage controlled oscillator that generates the cosine term for you, the carrier, and we have a shifter, phase shifter, which will turn it into a sine. We also use it to multiply the incoming signal. So we multiply the incoming signal both with a cosine, 2 cosine omega ct plus theta O is the output, and this is 2 sine omega ct plus theta 0. Okay, so they are exactly pi over 2 phase apart, these two signals. They have the same phase otherwise, other than this pi over 2. And then we pass this through a low pass filter. Pass this through a low pass filter again. Now what is the circuit doing? Now you should remember this from the PLL, that if you multiply an incoming cosine and sine, you should remember what happens. And then when you remember that, what you can again remember is this is the m of t cosine theta error, and here you get m of t cosine theta, sorry, this is the sine theta error. Okay, so this again you should remember from the PLL discussion. So I suggest you go back and remind yourself what happens if you multiply these two sinusoids, and then this is the output. Now we multiply these again. So we multiply these two cosine and sine theta e's. And what is theta e here? I should tell you what it is. So here theta e is the error phase, which is the difference between theta input and theta output. Okay, so this is the, again, same theta e as we discussed in PLL. So that's the same thing. Now you after multiplication, you pass what you get here. What do we get here? 1 over 2 m squared t, if you multiply these two, sine 2 theta e. So I'm gonna write it again here, 1 over 2 m squared t sine 2 theta e. This is what you get. And then you pass this through a low pass filter again, and then you give this as your input to the VCO. And the discussion is that here the input signal here is basically, after low pass filtering, can be written as r times sine 2 theta e. Okay, well, you can see it is you can see that here the m squared t in the input of the low pass filter again has a low pass component, which comes out like this. Okay, so now this if you make this input of your voltage controlled oscillator, what will happen is that if your error phase is high, then it will tend to increase. So you can analyze this again. You can just say that, okay, if theta e is high, this means what? Theta o is not high enough. Theta o is small. Okay, smaller than maybe theta I. Okay, then what will happen is that if theta e is high, the VCO output tend to increase VO. VCO output will increase theta o, and so on. So we compensate for the differences, and this is another kind of phase lock loop, but a separate different circuit, which is called the Costas loop, which can handle this synchronization issue when you don't have a carrier. Okay, so that's what you can do. That's another approach. So you can do either the first approach, which is signal squaring, or you can do the Costas loop, which will also handle this issue of carrier acquisition. How about in single sideband? So if you think about, so this was for the double sideband. Can we acquire carrier acquisition in single sideband? And I'm not going to go through the analysis, but I'm just going to say that it is not possible to acquire. So this is suppressed carrier, of course. Okay, no carrier is sent. So can we find the, it's not possible to acquire the carrier. So what's the solution then? If you cannot really solution, you can send the carrier. That's one. Maybe a pilot signal, what's called a pilot signal at the carrier. Okay, which you can use again just directly into a DLL after bandpass filter. Send, you need to send it carrier, or use a good crystal, good oscillator at the transmitter and receiver, so that you get this exact same frequency. But that's not a good approach because of the Doppler shifts and so on. So what is best is maybe to send a pilot signal, and then you can use PLL. After which we can use the PLL. Okay. This one is not a good approach. Okay, not a good approach due to Doppler shift and so on. Okay, so now this is the end of the discussion in chapter 4, and we are gonna move into amplitude. After amplitude modulation, we are gonna move into angle modulation in chapter 5, which I'm gonna start in a moment after this. Okay, so let's take a break now.